Alright guys, welcome back. It's time to introduce fully what the coefficient of restitution is now and the equation that we're going to be using and talk about how it affects different types of impact and collision problems. So we can write the coefficient of restitution equation like this. It's the coefficient is the lowercase e, and it is VB2 minus VA2 is all over VA1 minus VB1. So this is for two bodies A and B that are going to have an impact. So let me just draw that out right here. So if we take the right as the positive direction in all cases here, then in order for A and B to have an impact, then VA, this is VA1, must be bigger than VB1. By bigger, I mean like more positive, a value that's more like bigger in the positive direction. Like they can actually be physically moving towards each other, like A moving to the right and B moving to the left. Or if they're both moving to the right, then as long as VA1 is bigger than VB1, eventually they'll catch up and impact, and basically the distance between them will be shrinking, like their relative position or separation, if you will. And then regardless of which way they're going, as long as that separation is closing, they're going to impact. And then after impact, as long as they don't stick together, the separation is going to grow between them again. So in after impact, then basically VA2 is going to have to be less than VB2. When we consider to the right being the positive direction, then as long as this one is moving faster in this way than this one, then that separation is going to be growing. So if we want the relative velocity of the two bodies, then we subtract the smaller quantity so we can get a positive relative velocity. So on approach, the relative velocity is going to be VA1 minus VB1, and on separation, the relative velocity is going to be VB2 minus VA2. And that's exactly what you're seeing up here. VB2 minus VA2 and VA1 minus VB1. So that's just the relative velocity of the particle separation just after impact over the relative velocity of the particle's approach just before impact. Now what's actually happening in real life when two bodies collide like this is when they collide, they actually deform a little bit. And during that deformation, it's caused by a force from the impact, and that force is acting over a certain amount of time while it's deforming. So that certain amount of time, that period of time, is called the period of deformation, and that time multiplied by the force, that it's actually caused by, gives us what's called the deformation impulse. So there's an impulse on collision when the bodies are deforming, and then at some point it stops and it basically rebounds. As long as the materials don't get totally stuck together and just stay together, then as it releases that energy that it's previously absorbed, it's over a period of time. So we call that the period of restitution. And that period of time times the amount of force that's released is called the restitution impulse. So first we have a deformation impulse where they deform, and then we have a restitution impulse where the bodies release again. If those impulses are equal to each other, then we call that a perfectly elastic collision. And our coefficient of restitution will be equal to 1. So let's write that here. So E is equal to 1 for perfectly elastic. In this type of impact, no energy will be lost, absolutely none. All of the kinetic energy will be preserved, and the deformation impulse will be exactly equal to the restitution impulse. In real life, this is impossible. It will never happen, but at this level of physics, we can model problems, for demonstration purposes. If the bodies deform and then stick together completely, we're going to get what we call the coefficient of restitution being equal to 0. So this is the case where the restitution impulse is equal to 0 and the deformation impulse is some other value. In this type of situation, we have the maximum amount of energy lost from the collision, and the bodies will stick together perfectly. We'll model some car crash problems like this, where two bodies hit each other, stick together completely, and then move together as one. In those types of problems, the coefficient of restitution will be given a value of 0. And then there's the everything in between case. So if we have our value for coefficient of restitution greater than 0, but less than 1, this covers all other types of problems where some amount of energy is lost. And in this case, the deformation impulse will be larger than the restitution impulse, but the restitution impulse won't be 0. So yeah, I should label this when we have coefficient of restitution equals 0, we refer to this as perfectly plastic, or sometimes you hear it referred to as perfectly inelastic. It's the same thing. And then for these guys, we don't have a special name for them. It's just like normal problems, you know, everyday reality type things. So really, when you're using the coefficient of restitution equation, you don't really need to think too much about it. You don't really need to think all that much about the period of deformation and the period of restitution and all that stuff, or those impulses, because normally you'll just be given a value for it, or you'll be asked to find the value. In that case, you would know information about the relative velocities after impact, and if you don't know the relative velocities after impact, then basically you'll know the coefficient of restitution. It'll be given to you in the problems. But yeah, as I mentioned in the previous video, you're always going to want to apply the coefficient of restitution for motion along the line of impact. So if we're dealing with an oblique example, it's only for the component of the velocities that are in line with the line of impact. You'll see that in the next few videos when I go over an oblique example, or you can check the previous video where I introduced the types of impacts that we can have. Alright guys, thanks for watching, and I will see you in the next couple of videos where we'll go over some examples using the coefficient of restitution.